All right, time for another draftphysics.com. Debatephysics.com also, but debate is not easy to solicit or encourage or have some possibility of participating in, and that's really demonstrated at places like Shittopedia, where it's basically an edited journal of reality, and the editors are deaf, dumb, stupid, all that kind of stuff. I mean, they can talk, but they can't listen. And they certainly don't do any thinking thing. The dumb part is certainly there. And unfortunately, it's a collective, it's a group. If you're not part of the group, you get isolated, and they become insulated from you quickly enough. And so groupthink wins. Just all bad signs, bad cultural mechanisms. The culture, if you want to have a sustainable, good culture, it has to be able to be challenged. It has to prove itself. It has to show its integrity. It has to be, like the public servants, they have to be willing to be held to higher standards and higher scrutiny. And if they don't want that, then don't take the job. I mean, come on. Not complicated. So, in that atmosphere is what I have to exist in. And so the truth will be stifled and prevented from being heard by most people. So the very few people that can trickle in here and have the privilege, frankly, I mean, in a way, you are being privileged, I'm telling you. I'm just saying that I'm predicting, okay, that what I'm going to say here is going to be very close to the actual truth. Closer, much closer than conventional physics ideas. And, like the speed of force, the idea that it's a push universe, the idea that the small universe where the electrons and protons exist is really the only universe, and everything happens by those laws that govern the function of electrons and protons, and everything else just emerges out of that universe. And it's the only place there is any phenomenon, okay, that's real, that's actual cause and effect. That's where it's all happening. These are ideas that physics should have come to long ago, and it's just because they are group thinkers, because they are basically just a religious cult, that they can't think outside of any of those boxes, even though they can say things like, well, you have to think outside. They can say the words, but they don't do any of that. They're all arrogant, obnoxious pontificators, like Feynman, for example, who basically said, if I can't think of it, you can't think of it. You're not going to invent anything. I'm way smarter than all you people. If I haven't thought of it, it can't be thought of. And that's the attitude of the physicist. Obnoxious as it comes. So anyway, magnets. Okay, so there's subtleties to it, but I mean the first idea, the big idea, okay, the one I'm telling you, this is the truth, is that everything they call a field, okay, is made of the same stuff, and it's just a different pattern in that stuff. So I'm telling you the elemental universe has this stuff called bits of force, these little particles of force. Doesn't matter how you imagine them, really. I mean, you could even imagine them as little pieces of glitter, if that makes you happy. Little sparkly unicorns. You think of them as that, but they're really small, little discrete places in space, and they just move at the speed of light, and they have a straight line direction. So that's what the universe is made out of, is a chaos of them. And there's two kinds: black, white, red, blue, plus, minus, north, south, electron active, we could say, and proton active. Okay, ones that push protons and ones that push electrons. So that's all there is. The universe is full of this stuff. And the fact is that every single surface is also made of this stuff, okay, in different arrangements. And the atoms are made of electrons and protons, okay. So, sorry, shouldn't have said this stuff. It's activated by this stuff. So the force hits a surface, And if the surface is arranged with red here and blue there and blah, 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 it can make a pattern, okay? And that's all that's going to happen. And so the kinds of patterns you can have is like a photon, which is bits all going the same direction, okay, with a frequency. That is a distance between them. All right, and that's a photon. And then magnetism, the trick is that you have electrons and protons, and they radiate their own force bit, okay? So because of the way they function, that's explained in other videos, they they emit the counter force. You know, if a red force hits a blue thing, or a blue force hits a red thing, it is transferred into the red force. It goes through and is transferred and creates the red force. But anyway, so they're always radiating, and the fact is if you arrange them in such a way, all right, they create a reflection to the world. So the universe comes in with a pattern, all right, of force, and the fact is it reflects based on how that pattern matches the surface pattern of electrons and protons, and so it can reflect with, say, in this example, more blue going this way, okay, so there's some red in here, but there's more blue going this way, and more red reflects this way. So if something comes in this way, it's more likely to reflect red. If something comes in this way, it's more likely to reflect blue, okay. And that just has to do with going right through the thing too, in the sense that, as stated, you can have a circumstance where you could have blues, all right, arranged, a red comes in, and it comes out the other side as a blue, okay, and vice versa. You could have a blue come in, comes out as a red. So the idea is you're just creating a pattern. So when you look at this magnet from different perspectives, it's going to look different. That's the simple argument, that whatever's sitting out here, an electron or a proton, will see either something that's net attractive or something that's net repulsive, depending on how that field looks. And more precisely, if it's a dipole, okay, it will, that is an electron and a proton in close proximity, then that thing will orient itself, okay, where the attraction is maximized and the repulsion is minimized. So it will turn in the field to be as comfortable as possible, to be as close to the red, I mean the blue as it can get, and as far away from the opposite force as it can get. So, I mean the same force, sorry. The protons and electrons react to the force. The more red there is, the more the proton runs away. The more red there is for the blue thing, the closer it gets, because there's more force opposing it. Like I said, this has been explained in other videos. But that's really the nature of it. So the key point is this field created by the magnet is just a change in the energy's reflection. So the energy comes in with a pattern. The thing changes the pattern. It reflects the pattern different than the pattern that came in. And the difference in that pattern, the difference in where reds are and where blues are, can be seen by other objects, especially other objects that are polarized, that is, that have an electron and a proton side bias. And yeah, so that's probably enough. But there's nothing created by the magnet. The magnet isn't pushing stuff here and scooping stuff up here. Stuff isn't coming out one end and going in the other side, or any of that crap. None of that's, there's no movement in this external field besides the change in the pattern. That's all it can do, is change how it looks. So it's like an iridescent material. You look at it at different angles and the colors all change. Same thing for a magnet, except it's a standardized kind of change, and you know, a polarized change. So you look at one end, it looks red. If you look at another end, it looks blue. That kind of thing. But the field itself is just how something looks. So it's just like our world. We look at things and see what they are. We see them by seeing the energy hit them, and it comes back to us, the energy at the right frequency, and then we'll see this is red and we'll see this is bluish because of that frequency, because this thing has absorbed the red, okay, and this thing has absorbed the blue, all right? So the blue didn't reflect. The blue light went into the object, all right, but the red light didn't. It bounced off. This is doing the same thing. And so it's just a reflection to the world. And I can make this, really easy. I can switch their nature by just changing their surface chemistry a little. And the same is true for the magnet. You just change how the poles are arranged, and you change how it looks to the rest of the world, the rest of the universe. Yeah, so it's probably enough to begin and such. So the Wikipedia page. So the important fact is the magnet's not producing a field itself. It's just reflecting a field, and reflecting it changed from what it was when it came in. So it's not making magnetism, it's not making some new force. It's just changing the force that's hitting it. Yeah, so it's not making anything called energy. It's just changing how the energy is configured. Alright, a magnet is a material or object that produces a magnetic field. So again, produces is a tricky word, okay, but yes, okay, it's a magnetic field, but it's not really produced, it's just an artifact. It's not an artifact, it's just a property, a change in the property of the field. So it's just changing an existing field into one that now is polarized, that now has more blue one way and more red the other. A different appearance from different locations. The magnetic field is invisible, so all of the forces are invisible. We can't see photons until they terminate. We can't, they can't affect something unless you bang them into something. So I mean, it's pretty much showing us that you can't use a force unless you use the force. So you can't measure a force unless you consume some percentage of it. So that's the only way you can measure it or see it, is to force it to move electrons and protons. Without moving electrons and protons, you can't see a force, because you can't use a force to affect a force. So by that definition, obviously, when they state that light is bent by gravity, they're wrong. Okay, it's bent by electrons and protons. It's changed in its direction by interacting with electrons and protons. And if it doesn't interact with an electron or a proton, it's not changing its direction. Forces can't act on forces. Little bits of force are inert to each other. They need a piece of matter, to be the conduit, the catalyst for interaction. A force can only interact with a force by hitting a piece of matter, causing it to move, which causes it to reflect forces differently. But it is responsible for the most notable property of a magnet. Okay, the magnetic field is invisible, but is responsible for the most notable property of a magnet. So again, the change in the field is the notable property. That's all the magnet's doing, is changing how the object reflects the universe. So it's just changing its appearance. It looks different. A force that pulls on other ferromagnetic materials. So the pulling and pushing thing just has to do with aligning your dipoles. So if they're aligned wrong, same pole, they'll repel. If they're aligned opposite poles, they'll attract. And those are just the rules. Such as iron, steel, nickel, cobalt. Now the reason why it attracts iron, steel, nickel, or cobalt is because it turns those things into an opposite magnet. So when the rays of force hit the material, they cause the material to duplicate in completely inversely what the original magnetic thing is producing as a field. So if the field's blue it hits that surface, pushes the electrons. The protons are now more visible, and so it becomes an opposite polarized magnet. And so they attract only because iron, steel, nickel, cobalt can become magnetic. If they can't become magnetic, they can't be attracted. Okay, and attracts or repels other magnets. All right, a permanent magnet is an object made of material that is magnetized and creates its own persistent magnetic field. So I guess they could say a natural magnet versus a man-made magnet, or I guess you could make arguments about one's made in volcanoes versus this versus that. But the whole point is you can make nickel, cobalt, steel, iron. You can make substances magnetic by liquefying them, heating them in a magnetic field, and then allowing them to cool in that magnetic field, and then their little bits will orient to becoming magnetic. So the Earth's magnetic field creates magnets. An everyday example is a refrigerator magnet used to hold notes on the refrigerator door. It's not a very good example, frankly, just because those are kind of chaotic little magnets. You have a bunch of little magnets inside of a plasticine material. And so it's just really arranging a bunch of little magnets. All right. Materials that can be magnetized, which are also the ones that are strongly attracted to a magnet. Materials that can be magnetized, which are also ones that are strongly attracted to a magnet, are called ferromagnetic or ferrimagnetic. Anyway, so those are, like I said, you have to put some element of the iron and nickel and cobalt in this material, and I don't know if I'd call it an alloy because it's usually some sort of plastic. All right, such alloys of rare earth materials and some naturally occurring materials such as lodestone, although ferromagnetic and ferrimagnetic materials are the only ones attracted to a magnet strong enough to be commonly considered magnetic. Obviously, the Earth's magnetic field is pretty weak. So if you make a magnet in the Earth's magnetic field, it's not going to be very strong. But if you create a strong magnetic field and then make the magnet in that strong magnetic field, you get a much stronger magnet. Duh. Okay, all other substances respond weakly to magnetic fields by one of several other types of magnetism. So yes, aluminum and copper and some other metals, okay, you can induce magnetism, but it's a lot more forced. So you have to really push on them with a magnetic field to force them to become magnetic, and it's very unpermanent, so there won't be any residual magnetism. Ferromagnetic materials can be divided into magnetically soft materials like annealed iron, which can be magnetized but do not tend to stay magnetized. So you could say annealed would be soft. I don't know if it's the right word. I mean, annealed is, you can do two things. You can heat treat something by dipping it in oil, or you can dip it in water. You can do different things to cool a metal quickly. And so you can kind of fracture its internal substance, and that's why it's malleable, because it has a bunch of fractures in it. So it's more bendable. And then you can do, hardened steel. You can have the layers really close on top of each other. All the crystals are lined up, and it's more likely to be hard. Okay, and so stuff can't move around inside of it, the atoms. And magnetically hard materials, which do. Okay, so the hard materials can hold their magnetism, but all of them give it away to enough heat. So if you produce enough heat, you end up just breaking all the little magnets inside the big magnet. So I guess that's something they probably should have a little picture of here, which is that a material that's magnetic is basically made up of a bunch of little magnets. So you have a bunch of little magnets inside the big magnet. I mean, I don't know if drawing it as a checkerboard. right? So it's a checkerboard, red, black, and they're all lined up, so the reds are next to blacks always, okay? And all you're doing is saying, well, I can cut that anywhere, and I'll end up with a black bottom and a red top kind of thing. It's always going to be broken at a point where the magnets fracture, the little magnets, and so they'll always break. They're sitting on top of each other, north, south, north, south, north, south, north, south. You can understand if I break it somewhere, the little magnet's not going to break, the dipole. And so I'm always going to end up with a black here, a south. And there's always, no matter where I break it, the south is going to be what's the bottom now. And if I did the same thing at the top, I break off the top, I'm always going to break it with a red stuck showing. So no matter how I break it, I'm going to break it into another magnet. Maybe they don't believe that, but that's the simple explanation for why you can break a magnet and get two new magnets. All right. Let's see. Which permanent magnets are made from hard ferromagnetic materials such as, I don't know what this is, alincio and ferrite, that are subjected to special processing and strong magnetic field during manufacture to align their internal microcrystalline structure. So it's really just saying they're dipoles. So these are materials that are naturally polar. The atoms are polar. That is, the atoms are naturally have a side that's more electron and a side that's less electron. And so they have a side that's net positive and a side that's net negative. And you're really just saying that if I have them all aligned in chaos, then I end up with nothing, in terms of a pattern. I kill all the pattern. But the more I can align them up, the more of them I align in the same direction, I can create a bias where there's more pattern. And the higher the magnetic field I put them in, and the more pure the material, the stronger the magnet I can make, because all of the atoms will line up. All right, making them hard to demagnetize. To demagnetize a saturated, it's really irritating. To demagnetize a saturated magnet, a certain magnetic field must be applied, and this threshold depends on coercivity of the respective material. So all of them are sort of vulnerable to being hit hard. So if you hit them hard, you'll rearrange, all those atoms will turn a little bit because of the heat you're creating and the vibration. And so you'll degrade the magnetic effect because the pieces will start moving around and get stuck in patterns that aren't the same as the original pattern. So it's just like mixing the puzzle pieces up. The puzzle doesn't hold together very well. So if you shake it, you break all the little pieces apart and you've lost the continuity of your puzzle or something like that. Hard materials have high, whereas soft materials have low, whatever. Overall strength of a magnet is measured by its magnetic moment. Okay, which this is it's just nonsense. There's no magnetic moment. There's how much polarization there is, and then they say, or alternatively, the total magnetic flux it produces. So, why have two different concepts for the same thing? You're just saying how biased, how much of the polarization have I made visible because I have more stuff going this way, lined up this way, than I have stuff lined up that way. So I've created a bias in a direction in terms of the polarization of the atoms. An electromagnet is made from a coil of wire, so you don't need a coil. You just need a length of steel or some kind of conductor that acts as a magnet when an electric current passes through it, but stops being a magnet when the current stops. You get very little magnetism with a straight wire, but you get it. And the fact is, when you're coiling it, all you're doing really is intensifying the field on the inside, right? Because it's constantly reflecting into another piece of itself, another piece of the wire. So you're going to be more likely to retain your pattern because you're hitting it with the same pattern. That comes up again with the probably. I think when they talk about a horseshoe magnet. But stops being a magnet when the current stops. Often the coil is wrapped around a core of soft ferromagnetic material such as soft steel. So you need atoms to polarize. If you haven't produced any atoms to polarize, then all you have is the atoms in the coil of wire, and you can't make a very dense polarity out of that weak amount of material. So if you stick a piece of iron in and magnetize all of the iron, then obviously you're going to get a lot more effect for your in terms of have more atoms to polarize. And it's the number of atoms you have aligned that decides how much magnetism you're producing. So if you can force a piece of iron to become highly magnetic, then you're going to have a lot more magnetism. All right, which greatly enhances the magnetic field produced by the coil. So the coil is just making a magnet out of the steel. It's not much more complicated than that. It's maintaining, it's because it's creating a field around the atoms. It's a strong enough field to force all of the atoms to line up in that field. And so now you have a bunch of atoms all polarized in the same direction, and therefore more likely to create a visible pattern. All right, ancient people learned about magnetism from lodestone or magnetite, which are naturally magnetized pieces of iron ore. So I guess the point is it's only naturally magnetized by the core of the earth being magnetic, to some extent. So because the core of the earth, my guess would be, has some polarization because of the high pressure. You've got more neutrons, perhaps in the liquid center of the earth, and it's those neutrons that are creating the magnetic field, a polarization. The word magnetic was adopted in Middle English from Latin, who cares, lodestone, ultimately the Greek, blah, 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 meaning stone, whatever, is a place in, Magnesia, in Anatolia, where lodestones were found. Okay, and lodestones suspended so they could turn were the first magnetic compass. Earliest known surviving descriptions of magnets and their properties are from Anatolia, India, and China around 2,500 years ago. Okay, the properties of lodestones and their affinity for iron were written of by Pili of Elder in the Encyclopedia Naturalis Historia. Okay, fine, who cares? In the 11th century, so that's some kind of whatever, the 1200s, it was discovered that quenching red-hot iron in Earth's magnetic field would leave the iron permanently magnetized. This led to development of the navigational compass as described in Dream Pool Essays in 1088. All right, so it's all interesting that, they found out the compasses, they could make them a long time ago. They could take little shards of iron and, put them on a piece of cork and make a compass. Okay. Anyway, in 1820, Hans Christian Ørsted discovered that a compass needle is affected by a nearby electric current. So again, and it'll be more affected the more matter that you've polarized the atoms in. But anyway, in the same year, André Marie Ampère showed that iron can be magnetized by inserting it in an electrically fed solenoid. So he made a solenoid, I guess. A coil of wire, and led William Sturgeon to develop an iron core electromagnet in 1824. So I don't know where Faraday comes in here, but I don't see his name anywhere. Interesting. Joseph Henry further developed the electromagnet into a commercial product in the 1830s and 1831, giving people access to strong magnetic fields for the first time. So those were just big transformers, essentially. In 1831, he built, one side of a transformer. Just a lot of wire around a lot of metal. In 1831, he built an ore separator with an electromagnet capable of lifting 750 pounds. So that's impressive for 1831. But anyway, but it must have been quite a lot of wattage you had to pump into it. So anyway, all right, so magnetic field, let's see what it says here. The magnetic field density, also called magnetic field, the B field, or just magnetic field, is usually denoted B, okay, is a vector field. So I would argue that the fields, all fields are vector fields, and all fields are made out of lines of force, that is, stuff moving in straight lines. There are no, all of the field lines, the stuff you see with little curves and bends in it, none of that stuff is a relevant or meaningful property. The real lines of force are creating where those alignments are. So iron filings just turn into magnets, and you're just seeing where the magnets line up, where there's an equal potential in the field. And all of these little lines in this magnetic drawing, right? Can you see that drawing? Yeah, you can see enough of it over there. All the lines here are just a consequence of the fact that all of these iron filings are lining up in opposite to the north-south orientation of the original magnet. So they're all essentially opposite magnets. And so they're repelling each other. So each one of these lines is this magnet going in the same direction. So they're all repelling each other. That's why there's space between them. Okay, there's not special pathways. There's just creating a magnet, and you're creating a bunch of little tiny magnets, and they're all pointing the same direction, so they're all repelling each other. But if they connect, to their north-south ends, if they stick to each other north-south, then they won't repel. If they're this way, they repel. If they're this way, they stick. So they stick, and then they repel each other. And so those lines really don't mean anything. They're not they're not an indicator of some pathway or some force field or any of that. It's just that the lines of force, the red coming off of one end, you could argue, and the blue coming off of the other end, forces dipoles to line up in those orientations. Obviously, where there's a strong red force, they're all pointing with their red end down. I mean their blue end down. And where there's a strong blue force, they're pointing with their blue. Where there's a strong red force, they're pointing with their blue end down, and vice versa. And it just depends on how much that force is bent. How much they're exposed to get. As they get further away from the red end, the repulsive force gets weaker. Blah 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 blah. And so this is how they line up. But it's just an orientation to the field, and the actual force lines, the rays of force, are all straight lines. Okay. Someday that's going to be the understood truth. I'm just letting you know that force never moves in crooked lines. It's always in straight lines. So if something is moving a crooked line, it's because the field of the straight lines is changing in different locations. And that's why the thing orients itself differently, is because there's a different amount of the two fields in different locations. If I have a point A and a point B, and then I'm in a point some other place, I'm closer to B than I am to A, or I'm further away from B than I am to A. And so I'm going to have a different orientation because of my proximity to those 2 points. So as soon as you create a dipole, you create a signal that's essentially a blue light and a red light. Get far enough away, it looks like a purple light. All right, anyway. Its direction, which is along the orientation of a compass needle. Its magnitude, also called strength, which is proportional to how strongly the compass needle orients along that direction. So either you have a strong magnet in the needle, or else you have a strong magnetic big force that you're applying. But that's obviously the combination of the two is important. Now with the iron filings, they're all little pieces of iron. So if you use finer and finer pieces, you'll get a different lines. The pattern will be similar, but it won't be exactly in the same place. So every time you create a magnetic field pattern with iron filings, it's not going to be the same pattern, because the density of material is going to change, and you'll have an unevenness in that density. All right. Magnetic moment. So this is just really bad. There's no magnetic moment. Okay. Once you've polarized the atoms, they're polarized. They're not momenting. Okay. The magnetic moment, also called magnetic dipole moment, is usually denoted U. Is a vector that characterizes the magnet's overall magnetic properties. It tells you what the how it magnets its magnetism. Well, anyway, for a bar magnet, the direction of the magnetic moment points from the magnet's south pole to its north pole. So again, there's no moment. Okay, and the magnitude relates to how strong or how far apart these poles are. So how far apart the poles are just has to do with, you can sort of imagine that the overall strength of the magnet would probably be diluted, okay, if the material is very long. Like, you can't make a magnet that's 10 feet long. Well, I have to think about that. I don't know why you couldn't. I've never seen one, but... Alright, in SI units, the magnetic moment is specified in terms of AM squared, amperes times meter squared. So, obviously there's a strength to the field, but I don't think there's any point in qualifying it with energy terms, because it's really just the external field that has to produce the change in the field. So the energy is really something that was already in the field. So you're just measuring energy you didn't see before, because you now have a magnet to measure it with. A magnet both produces its own magnetic field and responds to magnetic fields. Obviously, the dipoles will turn each other. Okay, the strength of the magnetic field produced at very given points is proportional to the magnitude of the magnetic moment. So they're just, that's just saying nothing. That's just saying the word magnetic moment means the strength of the magnet. In addition, when a magnet is put into an external magnetic field produced by a different source, say a stronger source, it is subjected to a torque. So obviously the two magnets, if I put two magnets in proximity to each other, they're going to affect each other. They're going to be spewing a field at each other. And the fact is just like any momentum argument, whatever one's heavier or stronger is going to influence the one that's weaker more. Then the weaker one can affect the heavier one. But I suppose you could have a strong magnet that's lighter and a heavy magnet that is less magnetized, and then you're just stuck with the idea that you have to move more mass, so you can't have much of an effect on the thing that's very heavy and weakly magnetized. But the strongly magnetized light object will move a lot. Alright, a magnet may also be subject to a force driving it in one direction or another according to the positions and orientations of the magnet and the source. Obviously, if you can force the poles to be in a position but the magnet can't turn, then the force field will just push, or so to speak, pull. There is no pull though. If the field is uniform in space, the magnet is subjected to no net force. If the field is uniform in space, the magnet is subjected to no net force. Well, net force is a tricky word, right? Because there is force, it's just the two forces are balanced. It's pulling as much as it's pushing, even though there is no pull. Although it is subjected to a torque. So they're, at least in this case, they're conceding that they can't say there's no force. Like at that point where where you're affected by the moon's gravity as much as you're being affected by the Earth's gravity. That position in space, you could argue there's no net force, but there's plenty of force. A wire in the shape of a circle with an area A is carrying current. It has a magnetic moment of magnitude equal to whatever, IA. Anyway, the magnetization of a magnetic material is the local value of its magnetic moment per unit volume, usually denoted m. So this is just another way of describing the same thing, which is how strong is the magnet. With units, A divided by m is a vector field rather than just a vector, like the magnetic moment, because different areas of a magnet can be magnetized with different directions and strengths. For example, because the domains see below. How the magnetism is dispersed can also be variable. So yes, you can have a lot of continuity in the material in one location, and it's less continuity, and then there's more, and so that's how they make these refrigerator magnets. Often have a pattern built into the magnet of where it's strong magnet and then weak magnet. A good bar magnet may have, or even opposite magnets in the same material. So in parts of the material, the magnetic field is north-south, and then over here it's south-north, and then it's north-south, and you know. All right, a good bar magnet can have a magnetic moment of magnitude 0.1 am squared and a volume of 1 blah 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 blah, and therefore an average magnetization magnitude of is 1000 am. So again, just kind of blah, who knows. Iron can have a magnetization of around 1,000,000 amperes per meter. Such a large value explains why iron magnets are so effective at producing magnetic fields. Well, obviously the neodymium magnets seem to be more effective, but whatever. That seems kind of dated, frankly. Although two different models exist for magnets: magnetic poles and atomic currents. So this is sort of important. So their model, okay, really is terrible. They really don't have an explanation for how any of this stuff works. So they're going to call it magnetic poles, which isn't saying anything, and then atomic currents, which isn't going to be saying anything. There's no currents except the force, just like inside of us, when we absorb light, it's like we're absorbing the energy, and it goes inside of us and moves inside of us, and it's like a current. So you can call it a current, but it's really so chaotic that you wouldn't call it a current. So you can call heat a current of sorts, but it's obviously a very chaotic current. Okay, although for many purposes it is convenient to think of a magnet as having distinct poles, distinct north and south magnetic poles, the concept of poles should not be taken literally. I don't know why not. Okay, it seems clear that little dipoles make big dipoles, and it would be just kind of silly to say that an electron and a proton smashed next to each other is not a polar object. Clearly, it's polar. It is merely a way of referring to the two different ends of a magnet. Well, it's kind of a silly physics explanation. The magnet does not have distinct north or south particles of opposing sides. Yeah, it does really. Okay, I mean the only thing that can be causing magnetism is the arrangement of electrons and protons. So the same thing that causes what we call electrical polarization is the same thing creating magnetic polarization. It's just in a slightly different configuration. So you could argue that you could polarize something by, say if I had an object, and then the closer it becomes blue, and the further away it is, it's red. Well, I could squeeze it, and then I'd have blue, blue, and I'd have red, red. So you could argue that the electrical polarization, okay, is at a 90-degree angle. It's perpendicular. And that the magnetic one is clearly north-south. It's really just an electron and a proton. So it's the same magnetic monopoles. You're just creating a different appearance. So in one case, you're creating poles that are going south this way and north this way, and in the other case it's north-south. All right. the magnet does not have a distinct north and south particles on opposing sides. So it really does. The particles of electrons and protons are what create how something looks. So what the electrons and protons are excreting and their positions in the atoms will decide what color something looks from some angle. Okay, if a bar magnet is broken into two pieces in an attempt to separate the north and south poles, so obviously it'd be silly to think that the north and south poles are not created out of the atoms, and that you can't break the atoms. You're going to be breaking, at the seams where the atoms are. You're not going to be breaking atoms in half when you break it in half. So obviously, if the atoms are all polarized with their electron heavy side down or their electron heavy side up, and they're all in that orientation, then no matter where you break it, you're going to get a heavy side one way and a less heavy side the other way. Will result in it with two bar magnets, each of which has both a north and a south pole. So I think it's really wrong for them to say. They should just clearly say here, magnets are made out of little magnets. Magnets are not, until you get to a single electron and a single proton next to each other, which is kind of a neutron, the smallest dipole. All other magnets are made out of those little magnets lined up. Just like you can take a bunch of little magnets, stack them on top of each other, and make a big magnet. All right. However, a version of the magnetic pole approach is used by professional magneticians to design permanent magnets. So they just think of it as being polar for the purpose of designing, but it doesn't have anything to do with the truth necessarily. In this approach, the divergence of the magnetization inside the magnet is treated as a distribution of magnetic monopoles. So obviously, again, it's just kind of almost silly talk, right? So it says in particle physics, a magnetic monopole is a hypothetical elementary particle that is an isolated magnet with only one magnetic pole. A magnetic monopole would have a net north and south magnetic charge. So obviously these are the electrons and the protons. And the only thing that's complicated about the magnetic field is that it has a pattern. So if I said what's happening on the surface of a magnet is it makes a lot of bullseyes. Okay, so if you could really zoom in on a magnet, you're seeing a pattern where there's red in the center, and then blue, and then red, and then blue. And that would be a north pole target. And a south pole would have blue in the center, then red, then blue, so the two are creating a pattern, a visible pattern, and another magnet can see that pattern, can match that red and blue, the difference between those two targets. Okay, so it's the same force as photons. It's the same force as all the other forces, and it's just the fact that you're making it into a different pattern, and only something that can see patterns, that is only something that's a dipole, can see the difference between the red centered target and the blue centered target. Something has to have target vision, however you want to put that. Just like we can only see certain ranges of electromagnetic radiation, photons at certain frequencies, objects can see different things. And the fact is that a dipole can see that target. All right, this is a mathematical convenience, and this does not imply there are actual monopoles in the magnet. So there's no such thing as a monopole beyond the fact that just like the monopoles of electricity are just the fact that you have electrons and protons. So the monopoles are the northness of electrons and the southness of protons. If the magnetic pole distribution is known, then the pole model gives the magnetic field outside the magnet. The field B is proportional to H, while inside the magnetization must be added to H. An extension of this method that allows for internal magnetic changes to be used in theories of ferromagnetism. So who knows what those theories are? But wrong. I'm no doubt wrong. All right, so they say another model is the Ampere model, where all magnetization is due to the effect of microscopic or atomic circular bound currents. So this idea of continuous currents or energy, stuff where movement is generated inside the magnet, that's not what it's doing. It's just converting energy that comes in from the external world. So the external world puts energy in, and the magnet merely converts that energy, changes its distribution of where the red goes and where the blue goes. All right, circular bound currents, also called Amperean currents, throughout the material. For uniformly magnetized crystalline bar magnet, the net effect of the microscopic bound currents is to make the magnet behave as if there is a microscopic sheet of electric current flowing around the surface with local flow directions normal to the cylindrical axis. So none of that's happening. There's lots of force moving through all materials, all of us right now. Gravity's moving through us, lots of stuff's moving through us. And the fact is that depending on how the arrangement is, decides how the little pinball ball falls, how it bounces through us and how it comes out to the world. So stuff comes into us, and then we produce an outcome, and the outcome is dependent on how much arrangement there is in our structure. All right, microscopic currents in atoms inside the material are generally concealed by currents of neighboring atoms, so only the surface makes the net contribution. Well, obviously the only thing we see is the surface, but the surface is created. What the surface is doing is going to be created by what the interior is doing. Shading off the outer layer of a magnet will not destroy its magnetic field. Again, you can't shave anything off but extra magnets. So every big magnet is made of zillions of microscopic little magnets. And yes, you could shave some magnets off the surface, so what? Yeah, you didn't. It's all magnet all the way down. But we'll leave the new surface of uncancelled currents from the circular currents throughout the material. So there's no currents. The right-hand rule tells which direction positively charged current flows. However, current due to negatively charged electricity is far more prevalent in practice. So again, the right-hand rule is a consequence of that polar fact that I could squeeze a purple thing, and then I can make it blue here, and I'll make it red here and red here. That the poles won't be opposite. They'll be at right angles to each other. That's the right-hand rule. All right, in part anyway. All right, polarity. Let's see, where are we? 53 minutes. Yeah, let's see how far we can go here. The north pole of a magnet is defined as the pole that, when the magnet is freely suspended, points towards the Earth's north magnetic pole, which would be the north-south pole, but whatever, the real magnetic south. In the Arctic, the magnetic and geographic poles do not coincide. See magnetic declination. Since opposite poles, north and south, attract, the north magnetic pole is actually the south pole of the Earth's magnetic field. So obviously, yes, the magnet's pointing to the south magnetic pole because we've assigned the north side of the compass as the pointing side. Okay, as a practical matter, to tell which pole of the magnet is north and which is south, it is not necessary to use the Earth's magnetic field at all. For example, one method would be to compare it to an electromagnet whose poles can be identified by the right-hand rule, so you know which way the current went in. The magnetic field lines of a magnet are considered by convention to emerge from the magnet's north pole and re-enter at the south pole. So none of that happens. That is just it's wrong, and it's deceptive, and it's misleading, and it's a terrible interpretation of what you're seeing. There's no pathways. No piece of energy goes from one end and goes around the magnet and goes back in the other side. None of that happens. Nothing even close to that happens. There's just no currents, no movement, no motion, no anything following those paths. Doesn't happen. Alright, that's probably enough and such. So lots of ways to use electromagnets to do all kinds of interesting and fun things. Blah, 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 blah. Alright, so we'll call that a video then. And such. So till the next time, and doing my part. So I'm winding down on these Wikipedia videos. So I'll probably make other videos that are probably more efficient in terms of getting to the core subject and just explaining how I would argue what mistakes they have made, what wrong conclusions they've jumped to on terribly scant evidence. And that if you really do put all the facts together and you lay them all out on the table, you take all the puzzle pieces, you can really put the puzzle together. But if you only look at one puzzle piece at a time, you're going to have a real hard time putting the puzzle together. So anyway, getting the right answer. So they're doing it wrong, and that's why they've got a wrong model of the physical reality. And they're just so obnoxious and belligerent and kind of faith-based, kind of religious, jihadist, defensive overreactions to any kind of criticism. They just cannot allow their wonderful science to be at all tested.